Hello and a warm welcome to today's webinar where we will be previewing the MasterSeries 2023 major version increment and focusing on some of the highlights that you have to look forward to in this version. My name is Martin O'Gara. I'm a lead developer and director with Civil and Structural Computer Services. Most of you in attendance probably know that I do this type of presentation on the yearly basis as I lead up the development team and have a good understanding of all the various projects that the team has been working on and pulling that all together into a nice summarized fashion for you. My colleagues are waiting in the wings answering questions for today, so please feel free to type those questions as we go through the webinar. We will review those at the end, and anything that's not answered, we will do our best to answer those, and you will get correspondence of all those questions in the follow-up email from the webinar. This webinar has been recorded and it's going to be posted on all our usual channels, Vimeo, YouTube, and you'll also be sent a link to that when that's been processed. So MasterSeries 2023, you can access the full list of new features as usual by going to resources and what's new, looking at the 2023 major version increment new features, and you can peruse those at your leisure. We'll not be going through all of those today, you'll be glad to know, and we'll just be looking at some of the highlights. So getting straight into it, our first major new feature that you've probably seen some preview on is our Master Key concrete shear wall design. So that comes as part of our rebranded Master Key finite element slab and wall design module, which is an extension of our existing Master Key slab design. So that those features get incorporated into that module, and that module becomes an extended slab and wall. So we're going to be looking at finite element surfaces and how we design the shear wall components of those vertical wall finite element surfaces, particularly focusing on design aspects such as wall pier design, so the column-like design of the vertical components of the wall, and the wall coupling beam design, the bits of material above and below openings that connect wall piers together and do a pretty important job of transferring shear around your shear cores, and how we can design those. We will show you nice fast generation techniques for generating all of these different types of components within a large assembly of shear wall. And we'll be doing some nice auto design and showing you then how you can convey that design intent of your wall reinforcement through to DXF DWG design, with the scope of this module being to Eurocode 2 design. So let's have a look. We have a model on the screen here, a nice simple finite element multi-story concrete slab shear wall model with openings in the walls and a nice shear core arrangement. Let's go and take a look at just the shear core aspect on its own, filtering out the actual drawing of the finite elements themselves, the finite element nodes and members. So we've just gone into our design menu, into the wall design, and we're looking at our basic data and defaults. We've got some basic bar sizes for the wall piers, design methodology for wall piers, and auto design selection of spacings and bars. And the same thing for the wall coupling beams, some settings with regards to strut and tie, and the selection of bars that are going to be used during the auto design for the wall coupling beams. Okay, this is our interface, quite similar to the Master Key concrete slab design. We've got lists for piers and coupling beams, and you can switch between those. So let's generate our first wall pier zone, selecting the finite element surface that's going to be a part of, and then we can just draw that into position using our draw rectangle, which is really just the opposite diagonal corners of the wall pier. So the wall pier, column-like design of a wall, designing the vertical component with the various bending and shear aspects. So we can see the axial force in this wall pier split up into design strips, which we'll discuss in a little moment. And you can see the variation of the axial force across the wall strip, indicating that there's some moment involved. So let's have a quick look at our inputs. Geometrically, we have placed the wall, but it can be altered here with text input and can be anchored to nodes horizontally, split between levels vertically, and there's a bit of control there. Design methodology is probably the most important area that you want to keep your eye on, and the design method of pier subdivision that you choose. Here we're choosing equal pier strips split up into 1 meter widths. We can see how then that comes out, and we can see the various design forces that are in each of those strips in terms of axial, major minor moment, major minor shear. We have other design methods such as equal number of strips, but we do also then have a one zone design, which takes everything as one zone, which wouldn't really be appropriate for this, but it's useful to see that the major moment in this one zone design, 1600 kilonewton meter moment, and then the one zone getting about 3,200 kilonewton axial force. But as the design tells us in our design output, it's probably not a good idea to design this as one pier because its aspect ratio is a bit big, and splitting it up into wall strips gives you a more accurate design, picking up the variability of the force across the thing. So what you can see here is in the graphical drawing, we can see the wall strip, albeit we've set the fixed width to 1 meter. We can see our first strip is actually slightly less than that, and that's because we're choosing sensible design strips with the rounding to rebar strip methods. So this is our critical design force, and we're listing out here the slenderness of the wall and the slender moments that have been calculated for the slender wall, along with the nominal moment eccentricities. The design capacity is checked with a fully numerical biaxial bending moment, and with the full shear force and detailing checks in place there as well, checking max min areas of rebar and for the horizontal and vertical steel. And of course that continues for the other strips. So we've got a total of 6 strips here, and all of that design output repeats for that. So looking at the bars themselves, here we can see we've got the same bars throughout. We can draw the bars and on the model, and we can see the horizontal bars, the vertical bars, and how they're represented, which matches obviously what's been input. So for the vertical rebar, 16s and 200s, we're set to use the same rebars across all strips, which might be sensible. But if you do want that variability of control, you can then separate that out into specifying a different arrangement of reinforcement per strip, and the wall will get reconfigured for that, reconfiguring the strips slightly with the strip rounding to rebar spacings. So that's all on the local surface axis coordinate system, as we can see there. So we can take the strip, and we're just going to set that back to use the same rebars in all strips. Now, a strip is a column-like design. It wouldn't be appropriate to create a strip across the next level up because it's split by an opening. So we're going to create another wall pier zone, and this time we're just going to design a section of the wall that we would want to design. So that's one part of that, the other part being obviously the other side of the opening. So this is a design of a column-like design of this wall pier strip, which you certainly wouldn't include the part of the wall above the opening. So what we can see here is we've got a failure. So your standard MasterSeries design output with the cyan colored background indicating a failure. And this time the program's knowing that this is appropriately small to set up as a one zone design with a little bit of control in the basic data and default, saying if it's less than aspect ratio of 6, then default that to a one zone design. So moving on to our wall coupling beams, we're going to add a wall coupling beam to one of these regions that we've talked about. So just above these, between these wall piers. So the coupling beams doing the job of transferring the moment between the piers and are extremely important. We can look at here the bending moment diagram on the wall coupling beam, and you can see that's your classic moments applied to each end of the coupling beam. Now, with the coupling beam being an L over D of less than 2, as per our basic data and defaults, we're doing a strut and tie check as opposed to a standard beam check. So we can see the compression node design, the strut design with the transverse bursting check included, which takes account of all horizontal and vertical rebar, and obviously the tie check with that as well. If this were greater than L over D over 2, then you would get a standard beam bending section capacity check. So you have some design options in the coupling beam. Do you want to use compression rebar? Quite an important one for strut and tie is the amount of bearing of the truss into the wall, which can influence the size of the compression strut node of how much of the available wall you want to transfer that truss into. So I'm going to delete all of these because obviously if we continued on this basis, we would have to spend quite some time generating all of these. But thankfully, we've got our auto-generate wall zones, which does a quick job with some control and selecting all the appropriate finite element wall surfaces that we want these zones to be created on. And we can see here now the multiple wall pier zones, and we'll have a look in a second at the wall coupling beams. So all the green zones are the wall pier zones, the blue outline zones are the coupling beams. There's a few parapets at the top that were selected, but it's easy enough just to window select a multiple group of items. You can change their properties actually, or you can just, what I'm doing here, delete them in one file sweep. So we've got all our wall piers, lots and lots and lots of them, 56 minus the ones we deleted. Yeah, about 14 wall beam zones. I think there's a few excluded there because we had control over the aspect ratio that we wanted to include as well. So drawing all the reinforcement now for all the generated zones, both vertically, horizontally, we can see all of that coming in with the default arrangement of bars that we specified, remembering we haven't done any actual optimization or design yet. We can look at the unity ratio for the current reinforcement for both the axial moment or the shears, and here we're just looking at the unity ratios for the maximum reinforcement. So we've got some design issues there, small minor axis shear capacity problem there, same thing, only slightly more exaggerated in that top small little column. So perhaps the best strategy at this stage might be to do some design. Of course, you can do some manual design, you can change the things, or we can do some auto design. So you can auto design just the selected item or all piers or all coupling beams, or what we're doing here now is to auto design all of the beams, all the piers and the coupling beams, going through all of the design cases, selecting the critical one for each individual pier, coupling beam, and generating all of that. So that's now been optimized. I think we probably still have some problems in some of the zones simply because of some large design forces. So we can see we're now gone from 16s at 200s to 10s at 250. Not much problem here in any of the major unity ratios, all well within capacity. We can see really it's the minimum reinforcement that's driving these 10s at 250s here in this instance. A few areas where we've got greater than the minimum, we've got 25s and 250s here. A really useful trick is to be able to multi-select them, more than one item. We could window all of those quite easily as well. In the multi-select, you can make some really quick rationalizations. Selecting multiple items, you can quickly go and say, well, I would like all of these potentially to be the same reinforcement, so that you can quickly rationalize all your various different design regions to have some commonality. Small little 1% overstressing there. Let's have a look at a coupling beam. So we have our coupling beams here, and yeah, they all look good, and all the design has been done on them. This is an example of a coupling beam where the truss arrangement of loading hasn't been possible, and we're defaulting back to standard beam. So we can do design reports. We can also export the reinforcement to a DXF DWG output representing design intent. The 2D pictorial layout that you see can also be printed, which is useful, but this is a more generic design intent layout showing really what areas are attracting what quantities of rebar in terms of diameters and spacings for both the horizontal and the vertical steel, all exploded into a nice 2D arrangement. So that's our master key concrete finite element slab and wall design module, now covering shear wall design. Not part of the master key concrete finite element slab and wall design, but just part of MasterFrame finite element on its own. We have a new feature. We'll just squeeze this in here because it's related in a way. We have the MZZ in-plane moment derived from direct in-plane forces. When we look at a wall, we have obviously out-of-plane bending. The FE local surface axis is XY in plane and Z out of plane. So we have out-of-plane moments of MX, MY, but the MZ moment is the moment in the plane of the wall. And that's not actually directly given by finite element results, because that's you get more direct forces of what is the the fx and the fy in the plane of the wall as opposed to a moment. But those moments can be derived from that, and that's what our new MZ in-plane moment feature does as part of a section diagram. So let's have a look at that in action. So we have, oh, sorry, apologies. I'm just going to go back a slide and click on this guy to expand them out. So we have a wall here with some vertical and horizontal load to produce a deflected shape that we can anticipate. So looking at the graphical results of that and into the deflected shape, we can see, as we would expect, a wall shear in this manner. So looking at the contour of results, we can see the Fy, the axial force in the vertical direction, producing the sort of stresses in these piers that we would expect. Looking at the section diagrams of the Fy, we can see a little bit more clearly how that represents or is played out. And I'm just going to pause the video for just a second there because I think it's worthwhile explaining this in a little bit more detail. So we've got a distribution of Fy across the thickness of the pier, and that varies throughout the height of the pier. Obviously, if we were to take moments of these Fys about the center of this pier, we could develop an MZ moment, with the Z being the out of plane surface, out of plane direction for the finite element surface. And that's exactly what our MZZ section diagram does. So we just continue there. We have another set here, which I've previously set up for MZZ moments. So this is MZZ. You have to give it the width over which you want to integrate, which in this case is the 1 meter. We can see the moment now that's being created from that, and a similar type of moment then for the wall coupling beam. So you get that as part of your MasterFrame finite element, and you can see up here is the MZZ force component. Importantly, asking you to input the sectional width over which you want to integrate your in-plane direct forces to develop that MZZ moment. Okay, let's keep going. Next up, really nice one, MasterFrame material quantities reporting, which replaces our current frame statistics that we have in MasterFrame and is accessed in the same way. The big advantage here really is where our frame statistics focused on exclusively prismatic members, so beams, columns, bracing members as such, your 2D, two-noded elements. So you get all your section properties and your masses and such and lengths for those. However, our MasterFrame material quantities expands this notion to also include finite element surfaces, area loaded surfaces. The area loaded surfaces, you can do things like specify your deck profile, your thickness of your concrete, and from that all of the material quantities of the floor surfaces can be determined. You've also then got your foundation aspects of pad foundations and pal cap foundations now also included in this material quantities reporting. And really, the really nice thing, as we'll see in a second, is that it's got really good grouping and filtering facilities to make obviously the presentation of this much more extensive data easily accessible and presentable in the way that you want it to be, along with really nice things like choosing which columns you want to include. So you've got full customization over that output. So let's see it in action. So we have a nice big frame here. The frame statistics or the material quantities have already been called up. That's accessed in the same way from the little histogram icon on the top toolbar. So taking a second just to review the frame, quite a large frame, lots and lots of prismatic members, but we also have lots of shear core finite element surfaces. We have got pile cap foundations and lots of area loaded surfaces as well that give us much more quantities than we had previously. So looking at the interface, every single item, individual item, is now listed out with its various name, category, material section, and we would have them all here. And if we scroll down that list, you would see them all. However, we can filter to just certain aspects. So we can filter to just the prismatic members. We can filter to the finite element surfaces. We can see all the surfaces listed there with their properties. We can sort the list according to mass, so we can see potentially what is the biggest contributing, the largest finite element surface that has the most mass. Equally, then we can also look at the area loaded floor surfaces and see those. And again, look at the mass, and so we're looking at each individual area loading surface group that's split up per level, and how the quantities of that total. And also then we've got all the PalCap foundations and the volume of concrete associated with them, and the total mass, all of which are pretty consistent. Now, the really important thing is that obviously these individual quantities are great to have, but we want to see what the totals are, and this is where grouping comes into play. So we just filter back to prismatic members. We can group by material, and we can see now what the total weight of concrete, composite, and steel type members create. If we go for all the members and also include the category, we can see now we're grouping by category and material. So category being the prismatic, the surface, the area loading, and grouping also by material. So we've got prismatic steel sections, surface, or sorry, concrete prismatic sections, surface concrete members, and area loading concrete members. So you can see how the grouping comes into play there. A really nice one when you're looking at any of them is also to group by section. So section is the shape of the item involved, and the description of that. So we now have, just back to the prismatic members, we're looking at all the sections grouped. So here we can see that we've got 9 number 1250 by 650 members. Now let's have a look at the members that occur the most. So filtering by, or sorting by number, we can see we've got 744, 254, 102 members. And that's great. But really nice thing is also to group by length. We had some similar features to this in the last one, but this is much more controllable. And then now also grouping to length and material, we can see that we've got 451 6-meter long members and a smaller number of the 3-meter long members. Taking the length grouping off and sorting by mass and to the minimum mass, we can see really good way of identifying outliers of where you've only got a small quantity of, for example, that 254 102 22 kilogram. Would it be better to make that a 25 because there's so many of the others and so little of that? Those are really good tools for helping you make these decisions. Looking at the area loading surface here, then you can see, again, the groupings for material and section. So, but we can see in this instance, the grouping here, which really only relates to member groups, which is the prismatic members, the heading there that's not relevant can be deactivated, and you can really customize those reports. So a good bit of extra detail there in terms of the material quantity reporting. Okay, keeping the pace up. Next up, we've got Master Key Concrete Pad Foundation Design and a new feature for the Eurocode 7 direct method design approach. Now, up until this point, we've been using from EN 1997 Part 1, Clause 6.4, Paragraph 5 allows for something called a prescriptive method, which is really more along the lines of the ways in which pad foundations were traditionally designed. And when you've got a presumed bearing resistance is used to design the pad foundation, whereas Eurocode 7, and this is something we've been doing in our retaining wall module for a good few years, is the direct method. The direct method is a little bit more involved, whereby for the UK we're using design approach 1, and we have then the necessity to develop a more extensive arrangement of ultimate cases about which bearing and sliding and overturning and uplift are checked at the ultimate limit state. Previously in the prescriptive method, really you put in a safe working pressure for serviceability, for the controlling of the settlement of the foundation, and it was only the service cases that were used for checking for that bearing capacity, that serviceability bearing capacity. Whereas now with the direct method, you'll be checking for bearing capacity at the ultimate limit state. And not just one set of ultimate limit state cases, but we have something called combination 1 and combination 2 cases. Combination 1 being your action 1 and M1, action A1 and M1 being A1 being factored loads, and M1 being unfactored soil property factors. So that's one set, and the Eurocode 0 calls that set B. Another set is combination 2, where you've got A2 and M2, where A2 is much less factored loads, and M2 then is factored soil properties. So a different set of, or different way of looking at it, and that's really a set C cases for Eurocode 0. And these are the cases typically where bearing is more critical, because the increase of the factors in M2 versus M1 play a bigger role in reducing the soil bearing resistance than the reduction in the actions do. So you end up typically nearly always having critical bearing cases for combination 2 set C geo cases. Now, in this circumstance, the bearing resistance isn't an input value, it's a calculated value from the soil properties. And you can see how that's done from Annex D of the Eurocode 7 Part 1. So we'll have a look at how that plays out in just a moment or two. In addition to that, for overturning an uplift, you've got EQ cases, which are EC0 set A cases, which produce the right amount of, say, minimum dead load or favorable dead load, along with lateral loads to check for that uplift scenario. So let's have a look at that in action. So here's our sample model, and we're going to look at, this is in MasterFrame. Now this can also be done in standalone pad foundation, where it's all a bit more automated in terms of loading cases. But the first thing is really these loading cases do need to be generated as part of your MasterFrame model, otherwise the pad foundation won't be able to design for them. So these are our set B cases, which are the traditional cases that you would typically have been used to up until this point. Now this area we're looking at here is not new. This has been around in MasterFrame for quite some time, and indeed all the features that you're looking at here have been there for quite some time. So I have added an extra template in here of dead plus live combination 2 and choosing set C, so that will generate the appropriate cases. And another one for the EQ, which is down below, chosen to be EQ set A, with the dead loads being set as being favorable, and including just actually for wind direction 1 here, whereas probably should have been wind all. So that will generate a set of cases, which has already been done, and we'll just preview those cases. So lots and lots of set B cases here, and we probably really should have more set C cases. We've only one set C case here, but we probably could have dead plus live plus wind set C cases, and there would be lots more of them. And then a few combinations of the EQ cases for just wind direction 1, as we saw. So that could be much more extensive, but it'll give us a good enough idea of what then happens when we get into the pad foundation design with these few additional cases, and then how we control the usage of the new method. So we're doing a quick analysis here, and into the design, and we can see straight away from the output we're using the direct method, and we'll have a look at our output in a second or two just to see how that has influenced this. First thing really is just how do you control this? So into the basic data and defaults, over to the pads general area, and into the geotechnical section. We will have a look then at the Eurocode 7 design methodology can be selected there. So we're on the direct method, we can change to the prescriptive method. Just popping over to the prescriptive method, you can see the types of inputs that you've been familiar with: safe working pressure at service, your coefficient of sliding as a percentage. So these are all consistent with the previous inputs. However, with the direct method, you've got a good bit more at play here. There are advantages to this in terms of, I feel, in terms of the design economy that you'll be able to get out of this. Some control over which cases you want to check bearing on, if you want it just to be a little bit leaner. But so typically checking combination 2 set C is fine. You can say whether it's drained or undrained, and then the appropriate soil properties are presented for the drained or undrained condition. So angle of shear, angle of friction, which controls the sliding coefficient, and if you've got a cohesive soil, what the properties are there. Whether you want the pad depths to be included in the overburden, you really always would. Really important one here is your serviceability to ultimate limit state factor of safety, because these will develop ultimate bearing resistance capacities. And we need to know what would be an equivalent bearing resistance at service, and this is where this factor comes in, which really is a big enough factor to ensure that you're not going to get excess settlement at service, which is really what you're trying to do with the service case. Density of the soil is really important. Height of overburden is also really influential in terms of increasing the ultimate bearing resistance capacity, and not to be neglected. And I think it plays an even bigger role when calculating the soil bearing resistance to Annex D. So looking at our output now, we're explicitly saying we're using the direct method. We're saying we're doing the bearing check for the geo set C cases with M2 factors, and then we're spelling out how we're doing the settlement checks in the service cases with our factor of safety of settlement. Listing out some soil properties here. Now, if you didn't have any set C cases, we would still do the geo checks for set B cases. If you didn't have any EQ cases, we would do the overturning and uplift for those, and we would give you warning notes on the screen saying we couldn't find any set C cases or we couldn't find any set A cases. So we're looking at how the bearing resistance then, we're sort of saying the bearing resistance calculated from Annex D, and you might expect to see some output on the screen at this moment in time showing you what the bearing resistance capacity is. However, that is very much a numerical thing that has to be calculated on a pad by pad, load case by load case basis, because the size of the pad that's under pressure, the direction of the shear force, all come into play when calculating this bearing resistance. So you'll see the bearing resistance result for each individual load case, but not the detailed calculations because there's many, many of them. So let's look at our first critical serviceability case. So the critical serviceability case, load case 22, tells us we're calculating ultimate bearing resistance for M1 soil factors of a lovely big large 784 kilonewton per meter squared. Then that gets divided by our factor of safety for settlement that we input of 3, giving us a safe working pressure at service of 261, which thankfully in this instance is in excess of our bearing pressure value of 219.5 kilonewtons per meter. And then on to our ultimate STR case, which is strength. Differences being that, yes, you get the normal design in the section that you did, but you don't get the overturning or uplift or sliding checks done because it's really just an STR case. Our first geo case, our critical geo case, is load case 65, which is no surprise. I think we only had one set C load combination 2 case. And we can see down here from the bearing resistance output that using M2 factors, as we expect, a much lower 430 versus the 784 that we had above, all down to the M2 factors versus the M1 factors. So that's your, and then also you can see the sliding check being done with the sliding resistance calculated in accordance with Eurocode 7 with the appropriate factors at play. Then on to our equilibrium case. So our critical equilibrium case for overturning and uplift, no uplift in this instance, being listed out there. And that lists all the critical cases in those circumstances. Now, if we do just switch back to the prescriptive method, just so we can contrast the output, some changes here in that we're being much more explicit about the design methodology we're using and saying what the approach is. However, the design that follows is very much in accordance with the approaches used previously in your MasterSeries. If you have an existing file, it will continue to use this prescriptive method, so that won't automatically change on you. But if you do decide you want to take advantage of this, because I do think there's advantage to be had, then you can go and, if you have those soil properties, you can have those input and have that all calculated much more accurately. Okay, on to our master key connections. Master key connections, a few nice features for beam to column moment connections, where we previously only ever had I section to I section support. We now are doing hollow sections, square rectangular hollow sections for the beam sections, and on a similar vein for the beam to column moment connection. Maybe find it hard to visualize what that difference is in your mind, but we'll see in a second. The column now can be a hollow section as opposed to just an I section connecting to an I section beam. A nice new feature with a little caveat on the beam to beam simple connection supporting toe plates, which has been asked for quite some time. A little bit of thought is required on that score. So onto our little demo, a very simple frame which demonstrates all of these nice new features. Just to show you that this is our eaves beam to column moment connection where both elements are an I section, whereas on the other side we have a beam that's a hollow section connecting to an I section column, and you can see then the connection that's being produced in that scenario. So with the extended end plates and bolts in the extended end plates being the approach that's used. Now the CDEC rules with regards to the end plate bending for mode 2 and complete end plate yielding are all taken into account, which are slightly different from the normal end plate bending rules. So onto our column to beam connection, we can see that in this instance the column is a hollow section. So just clicking on that column, looking at the section types, as well as your I sections, you've got all the different square, rectangular, hollow section types that are part of whatever steel section open library that you're currently operating with in your model. So onto the beam-to-beam flexible end plate connection. We've had quite requests for it's a common feature these days where fabricators like to weld a toe plate onto the outside of the supporting beam from which to connect the supported beam. So we just simply turn on the toe plate setting, we can see that arrangement coming into place. And we've all the different inputs that allow you to control the thicknesses, the weld sizes, and so on. And you can see there's a considerably, a lot of additional input here, which is really a lot of extra output, with regards to the bending of the plates and the tying resistance. Probably one of the most important things to draw your attention to is the statement at the bottom, which has disappeared from the screen here now. But there's the statement really that, let me just actually pop that up again and we'll just zoom to the end so that we can see that. The supporting beam torsion is a significant aspect. Now, obviously, there's a bit of nominal eccentricity of design moment that gets created here, and that does get designed with regards to forces that are transferred through from the stiffening plate back to the section and so on. However, the beam itself may not be designed for this here, and we're really just warning you against that. I think it's often forgotten how poor I sections are in torsion, and how even a little bit of torsion moment can create a significant amount of torsional rotation. We don't necessarily know what that is. This could be a standalone connection. We don't really know if it was a standalone connection, where the connection is along the length of the member, what the end conditions are. So it's not something that can be calculated at connection design time, but it's something for the designer of the beam to be aware of, that this is being used. So that's a really important caveat to put into place there. Okay. Another nice feature in MasterKey steel design, we have, for certain types of members, this is really useful, the ability to view the physical drawing of the member in great detail with dimensions of the physical member versus the idealized node-to-node analytical member, including haunch details, including the positions of purlins and stays. So it's particularly useful in a portal frame rafter where you've got a lot of geometry going on, and where the purlins start with regards to the physical member depends on a lot, depends on the size of the column, depends on the thickness of the end plate. So we have our Show Purlin Designer icon here, which when we click on that, you get a pop out with a more physical view of that. And as you live input the different inputs for your, input your different lengths of lateral restraints, the physical diagram gets updated, and as you input in your positions of your stays, those are indicated as well with the red triangles that you see there. So the dimensioning of the haunches is quite useful there. You get an offset dimension there of what it is from the node to the start of the physical member, which helps you in terms of when you're putting in your distances to your lateral restraints, which are all from a nodal position. that helps you in terms of knowing where they will be in the physical member. And this output can be included in your design report as well on a per member basis if you want to select that to be part of a more detailed output. The end plate thicknesses actually can be specified and input at this stage as well, so that you can fine tune that at this stage to say, okay, well, I've got a 20 mil thick end plate or a 25 millimeter thick end plate, because that will ever so slightly change the starting point of the physical member of where these purlins are located. Just remains for me to say thank you very much for your time here today. We really appreciate you taking the time out today to stop by with us and have a look at what you've got to look forward to. And keep your eye out for your invitation to join the beta testing program. We would really appreciate your help with regards to your involvement with that. It makes all the difference in terms of getting these versions out as soon as we can. So thank you very much, and we look forward to seeing you at the next webinar.